Okay, hello. My name is Shayan Najidi. I'll be doing a couple guest lectures for this course. I'll be doing the lectures on the optical implementations that we consider. So in particular, we'll be looking at how optics can be used for quantum computing and quantum cryptography. So this is sort of two lectures, but given the online environment, we have some sort of flexibility with how we can structure it. So I'm going to be uploading the content all at once for the 2 weeks. And I'll post that and you can go through it at your own pace. One reason I like that is because I think it's useful to be able to pause the video at times. And if there's things that you might be stuck on, to try to think about it more. And then I'll use the usual lecture hours to answer questions on the video material. So let's begin. So an outline for how the lectures will be structured. 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 First, we're going to sort of have a foundation in optics. So we're going to look at the motivation for using optics. And then we're going to look at understanding how to describe photons and their states, and look at some optical elements that we'll be using to control the state of photons. From there, we'll look at how to generate and detect single photons. And this is really where the quantum enters the picture, if you will. We'll see that if we begin with a classical state and we use the same optical elements and we go and we do a detection, sort of like a classical optical detection, then we are not going to be able to get any quantum advantage. The quantum effects are able to be produced through us generating and detecting single photons. So this is the foundation for the lectures. From there, we'll have two different branches we'll look at. One is quantum computing and one is quantum crypto, or cryptography. And so with quantum computing, optics have been around as an idea for quantum computing since the very early days. But the initial proposals were focusing on using nonlinear elements. It was sort of thought that you need to use some type of nonlinear element to do 2-qubit gates. And as we'll sort of look at briefly, nonlinear optics are quite challenging. So a proposal that overcame that was linear optics quantum computing, which you may have heard of since you're at IQC. And it's found ways to use single photon sources and single photon detectors along with linear optical elements to do quantum computing. Another one that you also likely heard of if you're at IQC is quantum cryptography and quantum key distribution. It's one of the sort of practical applications of quantum technology that has been given a lot of attention in the last 10, 20 years. Also, going through these topics, I understand that this course attracts a wide cross-section of graduate students. I mean, I guess wide is still all within STEM, but we have people in math, engineering, and physics. So at times we'll be doing different asides on topics that might be trivial to some of you and non-trivial to others. So for example, we'll pause a little bit and just be clear about what a diode is when doing some photon detection things. The engineers might fall asleep at that time, but the mathematician people will be quite happy with that. Same with like quantum teleportation. The people who have done 710 will already know that and can maybe skip a couple slides there. And the people who are coming into this course, 750, who are engineers who haven't done 710 yet, will need that. So let's begin. So why use photons? Well, the most important thing is that they make for the best photos. So if you want to be Instagram famous and you also are in quantum computing, this is really the way to go. So here are some photos I've Googled, most of which look like something from Star Wars or Star Trek. This last one, oh, not this one. This one is, I think, the most ridiculously high-tech looking. Okay, so obviously that's not actually a reason. I hope sarcasm gets across on these videos. They do make for very impressive for photos. An actual reason to use them is that they can be controlled with standard optical devices, so with beam splitters, phase shifters. If you consider the other implementations that we've studied, so I think so far the first one we looked at was NMR and then superconducting. Is that the order? Yeah, that was the order. And as we'll also see with the next implementation we consider with trapped ions, the control is pretty complex. Like I can't just order a component online to control an NMR quantum computer and bring it into my room and start playing with it. But the optical devices used to control the quantum states are simple things you can just order online, and they operate at room temperature, which is incredibly convenient. So actually, yeah, that leads into this point. In general, there's no inherent need for low temperatures. We'll see one way that photons can be detected that uses low temperatures. But unlike NMR, superconducting, and ions, there's nothing that makes it absolutely necessary to have to operate at low temperatures. So, I mean, you've seen optical tables maybe before. In the lab tours, you go in and see them. There's not some, crazy cooling devices like when you go into the NMR lab and you see this huge tank. Or with the superconducting, when you see the massive dilution fridge, there's nothing like that needed for optics, which is definitely convenient. And so we'll see this is a bit of a double-edged sword, but photons interact very weakly with their environment. So they have great decoherence times. And that's why they've been used for quantum cryptography or quantum communication. You can transmit photons really well. I mean, actually, if you know anything about fiber optic cables, this doesn't come as a great surprise. The reason I say it's a double-edged sword, well, if it interacts weakly with its environment, it also actually interacts weakly with other photons. So photon-to-photon coupling is really a challenge. And that's sort of the main challenge we'll see in LOQC, linear optics quantum computing. Try to avoid acronyms, but some of them come up so much that I'll repeat them a few times in the beginning and hopefully you get comfortable with them too. So maybe you start using them. But yeah, with LOQC, we'll see that you have to be pretty clever to get the photons to couple. Okay, so there's two concepts we need to go over first before we can really get into looking at the optical elements. And I'm not sure how many of you this is familiar with. And I don't want to spend too much time on it because I really want to start talking about the tools and the implementations. But one thing to know is that the electromagnetic field is quantized. So in section 4.11 of the textbook that you guys have a draft of, there's a derivation there for how to get to the quantum harmonic oscillator description of the electromagnetic field. So essentially, how do you get from this Hamiltonian, which you have likely seen in like some electricity and magnetism course you've done before, to this Hamiltonian here? And so this Hamiltonian is quite familiar, thinking back to chapter 2 of the text and to the early lectures where we looked at the harmonic oscillator. This is just a sum of different quantum harmonic oscillators. The basic idea between how do you get from this Hamiltonian to that Hamiltonian, you write out the Hamiltonian electromagnetic field, identify conjugate variables, and you promote them to quantum operators. I mean, it's a very similar idea to what we did in superconducting when we were looking at the LC circuit and we went to quantize the LC circuit. It's sort of the same strategy, if you will. I mean, not exactly. It's a bit more complicated than that, but in 4.1.1, we sort of detail it, and it's a few pages, so recommend you going through that. Another thing that's important to take from this Hamiltonian, so one is that it's a harmonic oscillator. Two is that it's being summed over different photon modes. So we have heard the term mode before. I think an intuitive way to think of a mode is just some way to distinguish photons. I get this question a lot in the when we're doing the cryptography demos, and if we talk about quantization, electromagnetic field, and we talk about different photon modes. But there's different ways in which you can distinguish photons. So it can be with their wavelength / momentum. This direction is there, polarization is there. But I think it's sufficient for us, we're going to drop k and lambda there. You'll see why the k and lambda are there if you go through the derivation in the text. But when we're doing quantum crypto, we're doing quantum computing, we're not talking about photons at different modes. And so we're going to be able to ignore that. And we're just going to write the A dagger A's as creation and creation and annihilation operators for the same photon mode. Okay, polarization. So here we have two pictures at the bottom, and K depicts the direction that the electric field is moving. So this is just the electric field. The magnetic field here isn't drawn. And so the field is moving along K, and it oscillates orthogonal to K. Okay, so it's also a field. So in the last slide, we talked about how it's a quantum harmonic oscillator, and there's these discrete excitations from the harmonic oscillator. I mean, that's where the photon picture comes in. And now here, when we're talking about polarization, you can think of it as a degree of freedom of the photon. Or, I mean, more intuitively, you can think of it as a property of a wave. I have always struggled with reconciling these pictures, like trying to imagine the photon picture and the wave picture sort of at the same time in my head. I was given great comfort when listening to a lecture by Leonard Susskind, where he says it's not possible to picture both. So if you have a way of imagining it, let me know. But if Leonard Susskind can't do it, then I don't feel bad about me not being able to do it. And don't feel bad if you can't also do it. So anyways, so we have this field that's propagating, and it has the field is oscillating. And there's generally two types of polarization we can think about. So one is that it's oscillating along one axis. And so we can fix this axis, and we then assign names to it. So we can say, if it's up this way, it's vertical. If it's going this way, it's horizontal, or whatever. Another type of polarization is circular polarization. So this is if it's oscillating along two axes and it's out of phase. So then you'll have some sort of small component here and a big component this way. And then as this one's getting bigger, that one's getting smaller. And if you add those vectors together, you're going to see that it's a spiraling polarization. Somebody asked once if it's oscillating along two axes, but they're in phase. Well, if it's oscillating along two axes, but they're in phase, that's going to be the same as it being linear, just along a different axis. So that's polarization. So those two sort of basic elements of optics, that the field is quantized and comes in discrete packets, and that it has some polarization. We're going to sort of build everything else up from that. So let's talk a little bit about photons and optical elements. So photon states. So if we're going to be working with photons, they're going to be carrying our quantum information. We need some type of way to describe their states. So they're the eigenstates of the quantum harmonic oscillator. So they are, equivalently eigenstates of the number operator, A dagger A. So we can denote these states in terms of the number of photons. So 0 being the vacuum states, and then 1, 2, etc. So the 0, I think, just to be clear, some people might get confused on this, but the 0 ket isn't the 0 vector. 0 ket is the vacuum state. It's a minimum energy state. It is a photon state. So here, when we have, so these states will be defined by creation and annihilation operators. So the creation operator on some state n takes you to n+1 with some factor in front. And then the annihilation operator takes you down 1n. I mean, this should just all be reviewed from the math section we did. If you still have any confusion around that, I mean, you can ask me in office hours, but it's also there in the lecture notes and in chapter 2 of the text. But anyways, yeah, so if you have A here acting on 1, it takes you down to 0. If it acts on 0, it takes you to no state at all. There isn't like a -1 state. It's the minimum energy state. And if you try to annihilate that, you have the 0 vector mathematically, which is different than the 0 ket. again, if that's unclear, let me know, and I'm happy to chat about it. So these are examples of Fock states. So Fock states are states that are given with a definite number of quanta. So photon states that we'll be using are one example of them. And you can write them generally some n state as being built up in the vacuum state. You just take the vacuum state and you add many different excitations, so you get the number of quanta you want. So again, this is some more of about trying to reconcile different pictures. So because a lot of us are taught optics in high school, and we have pictures of optical systems, and we learn optics in second year E&M, and that picture gets refined. But not often have we thought about optics from the perspective of quantum mechanics, mainly if for the students coming in from math, or I assume the engineers don't have to do any quantum electrodynamic stuff. But anyways, a quantum description of an oscillating electromagnetic field is not a Fock state. So a Fock state with like many photons, so like, you take and you make it some huge number, that's not going to give you a, like you just add a bunch of photons together, you're not going to get a classical picture. I think sometimes people think that. They're like, okay, well, 1 photon, 2 photons, that's quantum, and then if you add enough photons, you eventually get something classical. That's not the case. And that comes from, I guess, just the incorrect association of quantum with small, where really quantum is coherent and things being in the same state. But anyways, and one way to convince yourself that it's not is take a Fock state of arbitrary n and calculate its electromagnetic field. And we do this in the text. And you'll see that the expectation of the electromagnetic field is 0, which doesn't make any sense. However, if you take a coherent state, which we've seen before, and that's an infinite superposition of these Fock states with different amplitudes, then you'll end up getting some, and take the expectation value of that with respect to the electric field, then you're going to get some oscillating value. And that's also done as an example in the text. And really the difference is that to get to some classical state, it's a combination of many different Fock states that do that. Not a coherent state such as a single Fock state. And I hope that that is clear enough. Okay, optical elements. So we have our photons. Our photons are described with these Fock states. And now we want to control them in different ways. So optical elements are just anything that manipulate the state of photons. So you guys interact with them, or sorry, everyone interacts with them on a day-to-day basis. So there's mirrors, lenses, filters, optical fibers. There's many different ways that you can control the state of a photon. So the elements that you're familiar with, you might not have thought of them as gates per se, but one way we can think about them as gates is we can fix their action with the optical element for some period of time. So for example, you have a, actually I guess all these elements are elements I'm going to introduce, but say you have some optical element, say a beam splitter. I'll describe what a beam splitter is in a second if you don't know what that is, but you have some element and it interacts with that, the photon interacts with that element for some fixed period of time, then you can describe that as a discrete gate, some fixed action, and we can write it in the same way we've been writing any gate that we've been doing. We can find optical elements that represent Hadamard gates or poly X gates, poly Y gates, whatever. And we'll see that. We'll give some examples of optical elements and how they can be described as gates. And then I said this before, maybe I'm reiterating it too much, because at first I felt like I didn't emphasize it enough, and then I went to refine the lectures, and maybe I'm overdoing it now. But the optical elements aren't what's adding the quantum to the system. It's the quantum effects come from the state of the photons or the measurement of the photons. I say or because there's some quantum implementations that are out there. So I mean, if you're at all familiar with what Xanadu does, like if you look at continuous variable quantum computing, they have they can use Gaussian states, or they can use sort of just classical states of light. They go through and work with classical just optical elements, and then in the end they are able to do something that is some quantum computing. And with the reason they're able to do that is because they have measurement devices that introduce the quantum behavior, the quantum effect. Okay, so there's the first tool, one that we're going to use a lot, are polarizers. There's many different ways to polarize light. So for example, a wire grid. But in general, what a polarizer is it takes light that has many different polarizations, and it just sort of picks one to come out. So there's the wire grid is one way to do this. It consists of many different thin slits, and the orthogonal components to those thin slits will interfere. So they'll either be absorbed or reflected. That's not shown in the picture, but they'll be absorbed and reflected, and then just the one polarization comes out. So those are polarizers. I mean, anyone who has sunglasses has used polarizers before. So wave plates. So a wave plate is another tool that we'll use, and it rotates a photon's polarization. So I just put up a lot at once. I apologize for that. I try not to put up a bunch of things all at once, because that's like, I've been told that's overwhelming. And actually, I would find it overwhelming as well. Anywho, this is the action of a wave plate. So we have this UWP, this unitary wave plate. It's parameterized with some theta. This is our action of our wave plate, or the representation of it as a matrix. And what we have here is our input state. So we have some photon, like the horizontal component and the vertical component of it. And what we want to come out is some rotation in this basis of polarization. So here we're working with a polarization basis, where the two orthogonal states are defined as the horizontal and the vertical component of the polarization. So as you'd expect, if we're doing a rotation in a basis, well, we use the rotation matrix. This is the 2x2 rotation matrix that this is consistent in other implementations, or just from linear algebra. And we can choose how much the wave plate is rotating the polarization. So you can parameterize that by theta. So we have some input polarization, and we choose our rotation, and we get some output polarization. Those are two tools for choosing polarization. So wave plates are an example of a very important class of optical element known as linear optical elements. And I mean, the name sort of says it all. The output of a linear optical element is a linear combination of its inputs. So we have some input modes, and these parameters here gives us for the different matrix elements, for if we're writing U as a matrix. And then we get some output here. So it's linear. Linear is good. It's our friend. Quantum mechanics, who love working with linear things. So the rest of the elements I'm going to talk about now are going to be all linear elements. I'm pretty sure they are. If they're not, I'll mention it. So a phase shifter. So a phase shifter is a way to change a mode's phase relative to another mode. So for example, say you're using spatial modes. So the way I'm distinguishing my two photons is that, I can have a photon here or a photon here. And this is my way of distinguishing them. So in the previous example, I had horizontal and vertical polarization being my way to distinguish the modes. But now I have it whether, say, it's moving down this optical fiber or if it's moving down that optical fiber. May have just broken my chair. Nope, we're good. Okay, so we're moving through the two different optical fibers. And so let's say we have at first that the two photons are in phase. So they're moving along, and then along one optical fiber's path, I put a piece of glass. And as it moves through that piece of glass, it has a different, it's going to accumulate a phase difference as it's going through this other medium. Because when it comes out, you can now see that the two are out of phase. So phase shifters, I mean, their name, I guess, says them all. They shift the phase of one of the modes. And we'll see, like, as you can see how it's written here. So we have our input, so whatever optical mode we have coming in here, and then we add some phase. And we can choose the phase. I mean, here we could choose the phase by increasing the size of the piece of glass, We could use a different material. So there's different ways to change the phase there. Okay, beam splitters. So beam splitters are another tool. We're going to see how they're used on spatial modes, and they can create superpositions. Okay, so the last time I say this, but it's not that the beam splitter does some like magical quantum thing and creates a superposition state. If I put coherent light through a beam splitter, I would just get coherent light out. But the goal of a beam splitter is to transmit some of the photons of one mode into the other. So you can imagine like a partial mirror. I think I draw it here. Yeah. So I have one mode coming into the partial mirror, and some of it will come through. Oops. And some of it will come through. And then some of it is going to be reflected. And it's the same for this other mode. Some of it will go through, some of it will be reflected. And I say some in quotes like that because, well, what if it's just one photon? Then you're going to create a superposition. But if it was just like some coherent state of light, then it would just, half that light would come out here and half of it would come out there, and it would be identical. Okay, so as you can see, the beam splitter has an effect of the rotation matrix with these extra terms for the phase. And so the theta gives us the degree of the partial reflection and transmission, and then phi gives us the phase that's added upon the reflection. So we can choose this phase to be 0, and then we just get our rotation matrix, and then choose theta to be pi by 4 to get a 50-50 beam splitter. So let's see how it acts on a state. So this state here describes, we have two modes, and there's a photon in the first mode, no photon in the second mode. How to see that? Well, we have our vacuum state, and we have an creation operator acting on the first mode. So we can see the action of the 50-50 beam splitter on this creation operator, and what it gives us back. So this would be the sort of as a vector 1, 0, and you have, you know, the 1, 0. I guess I should have drawn that there, but 1, 0 being acted upon by this matrix, and it gives us back these terms here. So we have one creation operator on the first mode, one on the second mode, with a normalization constraint, and then we get back this superposition state. It's very nice. And now we can do a second example. I think this one's kind of interesting in that if you now have one photon in each mode, so one in the first mode, one in the second mode, and then you apply the beam splitter, and you have to apply the beam splitter to each creation operator. And what you get out on one of the modes, so it's going to be the same action, except for this minus sign on one of the outputs. So you go through and expand this out. It's a difference of squares. What you find is that you either have two photons in the first mode or two photons in the second mode. Just kind of interesting. They come in one on each, and they go through the beam splitter, and now they both have to be together. It's like a cute little love story of photons. And this is the Hong-O-Mandel effect. Okay, so those are our linear optical elements we'll be playing with. There's beam splitters, polarizers, phase shifters. And we're going to see later on how we use these for quantum computing and quantum crypto. But what's important now is that you are familiar with the optical elements we've mentioned, and that you're comfortable seeing them written as matrices. So if either of those things are uncomfortable to you still, I would pause the video, maybe just go back, look at them again, maybe write them down and see, just have them on hand if they're confusing, because we're going to be using them not right away when we're looking at the single photon detectors and generators, but we will refer to them when we're looking at linear optics quantum computing. Okay, so this is where we sort of get into some physics. A lot of what we've been doing is just giving some math descriptions of physical things, but here we're going to actually do something a bit more physical, which is fun. So we want to have a single photon source. And you might think, actually, I don't know if you would think this, but some might think that, that shouldn't be so hard. I mean, we have photon sources all the time. We make many, many photons. How hard could it be to only create one? Well, I want you to pause the video and think about this. What are the properties that a good or an ideal single photon source would have? So pause, and I want you to write out every sort of ideal single photon source property. If we're in class, I would like wait a little bit, but I mean, you guys can just pause and unpause, and I'm still here, so I'll keep talking. So here are some properties of an ideal single photon source. Well, one might seem obvious, but you want a single photon. You don't want 2, 3, 4, etc. You want to be able to get just one. That's the first thing. Second is that we want them the moment we want them. So to be able to use these in algorithms, to put them in quantum computing, to do quantum crypto with it, we can't just wait for them to randomly appear whenever. So we, something like we press a button, get a photon. And we want the photon's properties to be sort of somewhat tailorable. So we want the photons to be able to move in the direction we want, and we want them to have the frequency we want. I guess I could have said this a bit more generally, as we want them to be in a desired mode, that we can control what mode the photons are produced in. And if we had all these properties, but it wasn't repeatable, so we can't create multiple sources that give us single photons the moment we want them with the right property, we can't really do much with it. Can't do experiments if you can't repeat things. So we need multiple sources with identical qualities. So these are the properties of an ideal single photon source. We'll look at two ways in which you could produce single photons and look at the pros and cons of them. So one is spontaneous emission. And this might be the first one you thought of, because it's one that you learned sort of early on. But you have some isolated two-level quantum system. And it has some energy gap. And what's nice here is that you can choose the energy gap to be such that matches the energy of the photon that you want to produce. The system absorbs the energy, and it gets into this metastable excited state. Now, a metastable excited state, it's sort of like, I'll give an analogy, and then I'll say why it's not exactly that. One analogy is that it's sort of like balancing a soccer ball in your head. I mean, you can hold it for a little bit, but eventually you're going to have to drop it. And so eventually the energy is going to drop to the lower level and it's going to emit a photon. I mean, to properly explain spontaneous emission, you need some quantum field theory. Quantum mechanics isn't enough alone to explain spontaneous emission. But I mean, you can just picture me with a soccer ball in my head, and I think you're okay. So it absorbs it, and then it emits it. So this is sort of nice that we can get the frequency we want. We just choose, we find a quantum system that gives us that gap. Some downsides, though. One obvious one is, isolated quantum systems aren't just super easy to come by. It takes some work to get. And the photon's emitted in a random direction. And I mean, there's ways to, my pros and cons lists aren't exhaustive. They're just to give some idea of the limitations of these. But one way you could mitigate this random direction is you can fix the direction with a nitrogen vacancy center in diamond. So I put an acronym there. Probably shouldn't have. NV isn't maybe common to all, but it's nitrogen vacancy centers in diamonds. Or you can use something known as quantum dots, and they provide some more structure. I mean, they have many other uses besides just this, but one thing you can do with them is add more structure for using them as a single photon source. The added structure, though, does limit the range of energies available, which could be a limitation. Another one is heralded single photons or spontaneous parametric down conversion. So what you do is you pump a nonlinear crystal here. I'm going to talk about nonlinearity actually in a moment, but here you have a crystal where it has like two gaps, and the gaps between the energy levels aren't constant. So you have some nonlinear crystal. And so you're dealing with nonlinear optics. So we need to work at incredibly high energies, and you are pumping the nonlinear crystal. I mean, I guess you can work at lower energies, but then it'll work at a lower probability. I'll explain this all again once I get sort of all the information out there to you and the picture drawn. But the idea is you pump a nonlinear crystal, excites the crystal, and then as it decays through two energy levels. Due to the conservation of momentum, the trajectory is going to be fixed, so we know where they're going to come out. And what we do is that there's a signal photon that gets detected. And we put maybe like a sensor here in front of the signal photon. When that detector goes off, we then know that there's another photon here. And this is the photon that we use for our experiment. That's the one we use. Okay, so probe, it is a single photon. We get the direction and the frequency that we want, which is nice. The challenge is, and this is what I was sort of alluding to earlier, I sort of jumped to it, but it's that most photons pass through the crystal. And so the issue then is like really how on demand is it? I mean, I'm sure there's ways that you can improve upon this. And I think this is actually a very strong technique and one that is commonly used in the quantum optics community. A brief aside on nonlinear optics. Some of you may already know what this is, but I've just mentioned linear optics, nonlinear optics, and not a lot, and it might be somewhat confusing. So linear optics is sort of the optics that you've been used to. So materials, to a good approximation, respond linearly to fields. So what do I mean by that? Well, it's really the combination of three properties. And one of them is that you have one frequency of light comes in, and the same frequency of light comes out of your thing. So you come into a material, and when you come out of the material, the frequency of light's the same. If the material takes the state A to B and C to D, then A plus B gets mapped to C plus D. That's just, I guess, a roundabout way of describing like a linear action mathematically. And that if I increase the intensity of the input, the only thing I'm going to do is increase the intensity of the output. That's the only change. So what happens if I go to nonlinear optics? So at very high intensities, materials deviate from this. So, I mean, as far as I understand, all materials do. Maybe some do at lower intensities than others. Yeah, all do, because even vacuums will if the field is high enough. So you can try to choose a material where you don't need as high of an intensity, but generally you need very high intensities to work with nonlinear optics. And what happens is that there's actually a bunch of really interesting effects. The Wikipedia page has a bunch of different experiments and things that have been done and effects that have been seen with nonlinear optics, which are pretty neat, and it's an active area of research. But for example, you can have one frequency in and many possible ones come out. You get neat effects like 2-photon absorption. What I sort of said, one frequency in, possibly many out. You could do second harmonic generation. So you have some frequency of light in and a different one out. So the main takeaway here is that linear optics is what you're familiar with, and it has the nice properties you're used to using. Nonlinear optics can do some very cool things, but it needs incredible high intensities to be able to work at, and it makes it practically and experimentally, it's practically challenging, or at least significantly more challenging than just working with linear optics. Okay, so we did our single photon sources. Now we're gonna do the same thing with single photon detectors. So actually first, what is a photon detector? In general, it's just something that converts an optical signal to an electrical signal. So I mean, an eyeball is an example of something that converts an optical signal to an electrical signal. There's many other ones, sort of like an LED light in reverse. An LED converts electrical to optical, just think of that, but backwards. So here we want an ideal single photon detector. So I want you to do the same thing again, pause the video, and write down all the features you would have in your ideal single photon detector. This should be connected. Single photon should be one word there. Okay, so I'm not going to wait because you can just pause and unpause the video. So here are the properties of an ideal single photon detector. So one is that they're sensitive enough to respond to one photon. I mean, it's not a very good single photon detector if it only detects, 10 or more photons. So you should actually be able to detect a single photon. Another is that you want to be able to avoid counts from random fluctuations. So these are called dark counts. Mostly they're from thermal fluctuations. As far as I know, they're just from thermal fluctuations, but I guess maybe like a quantum fluctuation could cause a dark count. You need like an incredibly sensitive tool to do that, but I don't know, maybe it's possible. But in general, like if you have some thermal noise in the environment and it causes a fluctuation in the system, you don't want it to think that there's a photon there when it's not. One is that another is that you want to be able to detect the right frequency. So there's going to be background radiation in your environment, and you don't want your photon detector to respond to that background radiation. And one that, I mean, we sort of mentioned this by saying it's sensitive enough to respond to one photon, but ideally you could distinguish one photon from two. So if you have a moment, or two from three, etc. But if you have single photon sources that aren't perfect, or you have some noise in your system, there's a chance that sometimes there's going to be two photons there. Or actually, there's just sometimes where you want to detect two photons. So ideally, you'll be able to distinguish one photon from two photons. And this is the biggest challenge of them so far. Technologically, the first three elements have been achieved with good success. But sort of the next frontier is reliable distinguishing one photon from two. So generally, there's two approaches to this. One is the more traditional photoelectric effect. So the photoelectric effect, it's what got Einstein his Nobel Prize. It's if you have some metal plate and there's these electrons that are bound to it, you shine photons on it, and if the photons have above a certain threshold frequency, they have enough energy to liberate the electron. So you can imagine the electrons like tied to the metal with some chain, and if you shoot it with like photons that are, I don't know, like little Nerf balls, they're not going to have energy to break the chain no matter how many of them you put. But even like a single massive bowling ball being thrown at it will break the chain. So it's not about how much energy the photons have, or it's not about how many photons there are, which is saying the same thing. But it's about, you need the more energy to come from the photon packets having more energy. And so if you have that case, if it's above a certain threshold, if it's strong enough to break the chain, then it's going to liberate electrons. So another way to do it is through heat changes. Heat and current changes. Essentially, maybe I'll say it like this. It's with the use of superconducting materials. So take it like this. There's the photoelectric way to go about it, and then there's the way to go about it using superconducting materials. Now, using superconducting materials, one drawback is we lose a little bit of that strength of photons, and that we don't need to work at really low temperatures. But there's times where that's going to be worth it to do. So let's look at an example or two of each. Actually, I think we're going to look at two examples of each. One that's pretty intuitive is a photomultiplier tube. So a photon hits a photocathode and it releases an electron. For those who don't know what a photocathode is, an electrode is just a conductor that interacts with something non-metallic. A cathode is an electrode that is going to give electrons instead of take electrons. A photocathode is then something that is a cathode that is optically stimulated. So anyway, so a photon hits a photocathode and it releases an electron. This electron gets accelerated to another cathode, hits that, more electrons are released. So you get more electrons, hit it again, more electrons, repeat, 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 repeat. And eventually you get a detectable signal. So you get, through 10 stages, 10 to the 6 times amplification. So you get this single photon that has enough energy to cause an electron to be released from the photocathode, and what you end up getting is a detectable signal. So an aside on semiconductors and diodes. engineers are going to say, how is a slide on semiconductors in a graduate course? Mathematicians are going to say, thank you, I have heard this term a bajillion times and I've never taken the time to understand what it is. So I'm going to give you the 3-minute summary of it. Okay, so insulators stop currents from flowing, conductors allow them to flow. A semiconductor is an insulator at room temperature, but it becomes a conductor when it's heated. I mean, there's other ways to do it. You can also illuminate it. You can apply a current. You can use a magnetic field. But I mean, let's just keep it simple and say when you heat it, it becomes a conductor. To understand their operation, we need to know the basics of band diagrams. So I'm assuming everyone knows that atoms have energy. Okay, you all know atoms have energy levels. Trillions of atoms together instead have energy bands. So you take all these levels, you smush them all together with a bunch of different atoms, and these lines sort of like blend together and you get bands of for the energy. So here we have an insulator and it has these gaps between its bands. It's called a band gap. So because there's the gap, the valence band gets filled with all the electrons. And this gap is too big, the electrons can't just jump it. With a conductor, the bands are touching or overlapping, and so the electrons can move freely. This band's called the conduction band. Yeah, so the insulator, the large band gap, electrons can't make this jump. Conductors, no band gap. Semiconductors, there's a medium gap. And so the electrons can flow, but they just need a little extra push. So that's a semiconductor. Okay, so semiconductors are pretty boring on their own. So to make them interesting, we will dope them. So this is not the type of doping that gets you banned from the Olympics. So doping a semiconductor means adding impurities to it to change its electrical properties. So the first type of doping we'll look at is N-type. This is a semiconductor that's doped to have more free electrons. So the goal is to add more electrons without changing the total charge. I mean, we can't just pump a semiconductor up with electrons because as soon as it interacts with anything else, I mean, the electrons are going to leave as soon as they get a chance to leave. So we want to keep the total charge the same, but add free electrons. So how do we do that? Well, let's take a semiconductor that's made of just silicon, for example. So we have all the silicon lined up, and it's got these, it's like a puzzle piece here. If you slide these together, they'll line up and they'll create covalent bonds, and then the two silicons will share these two electrons. So imagine this phosphorus was in here. It would just be a bunch of silicons connected together with pairs of electrons. Now you put a phosphorus in and it has an extra valent electron. So when it goes and creates a bond with the silicon, it now is a positive ion inside of the semiconductor with a valent electron sort of floating around it and floating through the semiconductor. So now our semiconductor has these impurities in it, which are these positive ions. And for each of these impurities, there's an associated valent electron, or maybe not associated, but there's one more valence electron in the semiconductor. So we add ions and we add free electrons. A p-type is the same thing, but it's doped to have more holes. So holes are like the opposite of electrons. So you go and you do the same structure, but now there's room for a free electron to be there instead of having an extra free electron. So a p-type consists of negative ions and holes. So we take the p-type and we take the n-type and we put them together in contact. So we have this picture here, my beautifully made PowerPoint picture of p-type and an n-type connected together. And then when you bring them in contact, the electrons/holes are going to diffuse throughout the other regions. So here you have these free electrons, and they're going to be diffuse a little bit towards the p-type, and the holes are going to diffuse into the n-type. And so as they diffuse, oh yeah, check out the special effects. So as they diffuse, there's going to be a charge difference built up in this central section. And so as this charge difference builds up, an electric field is going to form. And so if you, in this middle section where they're connecting, all these free charges, so the electrons and the holes, have been pushed out of it, and the electric field has built. And so this region is called the depletion region. It just has ions and it has no free charges moving around, and it has an electric field difference across it, or a potential difference across it. So an electric field is there. And so yeah, so that buildup is repelling the charges, so they're both on their own side. Okay, so we have our PN junction. You know some basic diodes now. The engineer people can wake up again. And we're going to look at how to use one as a single photon detector. So there's something called an avalanche photodiode. And so we have our P-type junction, or P-type semiconductor here, our N-type semiconductor here. We have this depletion region in the middle. And with these, you can add an insulator in between. So you sandwich it in the middle and sort of in your depletion region. But I mean, that's not so important. I'm just putting that in to be sort of technically accurate, but you can understand the physics of what's happening with just a PN junction picture in your mind. So we apply a reverse bias. So we apply a voltage that's going to widen the depletion region. So if you remember on this side here, we're going to have some loose electrons, and the electrons are going to be, oh, sorry, not electrons, holes. We're going to have some extra holes, and the holes are going to be attracted to this negative terminal. So they're moving this way. And then here, it's the electrons that are going to be attracted to this positive terminal here. So you're going to pull apart, we get a larger region with just ions in the middle. A photon is going to enter the depletion region, hit one of the ions, and spring free an electron, or an electron hole pair, if you will. The field difference is going to pull them apart from one another outside of the depletion region into either end of the P-type or the N-type semiconductor. As it's being pulled, it's going to collide with other ions, releasing more electrons and hole pairs, and eventually you're going to have a detectable current. And so the electron, yeah, gets pulled by the high field, has high energy, kicks and releases other electrons, and you get the detectable signal. So the photons come in here into the depletion region, liberate electrons, and then you get an avalanche effect. So it's called an avalanche photodiode. That's your single photon detectors that use the photoelectric effect. Another type are superconducting photon detectors, which are pretty neat. So, I mean, you're probably pretty familiar with superconductivity now, since we just did superconducting qubits, but it's important to remember that the internal resistance of a superconductor drops. And actually, to be more general, the superconducting properties of a superconductor are present when it's below a critical temperature and below a critical current. So the temperature gets too high or the current gets too big, it breaks superconductivity. And each of these types of breaking can be used to detect photons. So one is superconducting nanowire single photon detectors. And so these have this sort of thin meandering structure, sort of like a potato masher, like thin little wires. And it's held far below its critical temperature, but close to the critical current. So what happens is when a photon comes and interacts with this nano-thin wire, it breaks some of the Cooper pairs by pushing the current over the critical current. And so you lose superconductivity. So if a single photon, so since a single photon is strong enough to increase the current past the critical current and break the Cooper pairs, a single photon is enough to lose superconductivity. And so once you've lost superconductivity, you detected a photon. The issue is one photon can do it, but so can two. So you can't resolve one from two photons. Another technology known as transition edge sensors, they'll take a solid piece of superconducting material. So this isn't some thin meandering structure. And they hold it, I think I have a picture for this. They hold it at the steepest point of temperature change. So you have your superconductor and its internal resistance here sort of depicted as decaying the function of temperature, and then it suddenly drops. I mean, this isn't a perfectly straight down line. I mean, it's close, but it's got some small, maybe it's like an 89-degree angle or something. And the superconductor is temperature it's held at the point of its steepest descent. And so what happens is that a single photon raises its temperature and creates a notable change in resistance. So in this interval of temperature, a single photon can make a sizable change in resistance. What's neat about these is that they can resolve one photon from two. There's sort of, you can think of it as enough room here on this line that one photon moves you from here to here, and then two photons moves you from here to like there, let's say. So they're able to resolve one photon from two. So that's it with our sort of foundational stuff on photon states, the single photon detectors, single photon sources, and linear optical elements. We have all the tools in our toolbox now to put them together to do linear optics quantum computing and to do quantum cryptography. So we're going to look at both of those now. So as you're familiar now, to have a physical system be used as a quantum computer, it needs to satisfy the DiVincenzo criteria. So I'm going to start by going over how a linear optics quantum computer satisfies the DiVincenzo criteria. So we want a scalable and well-characterized qubit. So remember, a well-characterized qubit is one that stays in its encoded space. And scalability is, you're able to, with a reasonable amount of resources, keep increasing the size of the number of qubits. So our qubit we have our photon that's going to be encoded, and we're going to use the dual rail encoding. So in this one, the 1 qubit state will represent the photon being in one rail, and the other qubit state will represent the photon being in the other rail. And in scalability, well, we have single photon detectors, so we just line up a whole bunch of, single photon sources, so we just line up a whole bunch of them. So initialization, I mean, it just goes right, the photon's produced and enters the rail, so nothing extra we need to do there. The gates we'll have to look at. So we have 1 qubit gates and 2 qubit gates, and we'll see how these are done with phase shifters and beam splitters. And then we'll get to the heart of linear optics quantum computing, LOQC, and that's the 2 qubit gate. Measurements, we just need to know which rail the photon is in, so we can use single photon detectors. And then we need large decoherence to gate times. I won't really talk about this because decoherence times in photons are huge. I will talk a little bit about the types of errors though that can be introduced and how those errors limit the 1 and 2 qubit gate times. But based on what we've covered already, we already have the scalable well-characterized qubit. We'll talk a little bit about the encoding, but we have the scalability part, how that happens. We know how to initialize, and we know how to measure. So let's look a little bit at this dual rail qubit encoding. So first of all, there's many ways in which we can encode a qubit. You just pick 2 orthogonal degrees of freedom and encode them as your 0 and 1 state. So you pick your degrees of freedom. So here, like I mentioned, it's going to be the dual rail encoding, and it looks something like this. So if we imagine our 2 photons traveling in 2 rails above one another, does that make sense? 2 rails in parallel, okay, that makes sense. The photon being in the top rail is going to be the logical 1 state. We can also write it as 1, 0 when we're being clear that we're talking about the 2 different rails. So I want to make this, sort of hammer this home, that these are all the same way, these are all different ways of writing the same thing. So a qubit in the logical 1 state is the photon in the top rail. It's equal to 1 photon in the first rail, 0 photons in the second rail. So if we want to write this with creation and annihilation operators, And so obviously 0, which is the other one. We would write this with a creation operator. Here it's on the second mode. Here it's on the first mode. So that's the 0 and 1 state. Similarly, we can have our plus and minus state and our plus I and minus I state. So we have eigenstates of all the Pauli matrices. And it just corresponds to different linear combinations of the creation operators acting on the vacuum state. So that's that. So 1 qubit control. So to do single qubit gates here, the way we're going to achieve universal 1 qubit control is by being able to do arbitrary rotations around 2 axes of the Bloch sphere. So as long as we can do, or what it's going to be here, it's going to be the Y gate and the Z gate, and we're going to parameterize them with a continuous parameter, which corresponds to continual rotations around the Bloch sphere. And with the 2 of those, we'll be able to do any gate. I mean, it's like a globe. If you can spin it on 2 axes, you can configure the globe in any way. So let's first look at how the Z gate is done. So we're done with the phase shifter. So we can put a material with a different index of refraction on one of the rails, wherever we need such a gate to happen. So it would look something like this. And we had this from before. Earlier on, we introduced the phase shifter. And it's parameterized here by this phi, which is going to tell us how much, the degree to which the phase is going to be shifted. So let's look at an example. I just put sort of arbitrary coefficients in here to write things somewhat generally. I guess it's a little bit confusing here because I have A2 and A1. Maybe the other order would have been nicer, but with A2 and A1, so this is just a qubit, or sorry, a photon on each of these rails. So this is some, could be some superposition, I guess, some factor of them with the alpha and betas in front. So we have our superposition of a photon in the first rail and the second rail here. We then go and we apply this phase shifter gate. And so it's going to, so as the operation of it, as we know, it's going to work on, it's just being applied on the first rail. I mean, there is no phase shifter here, so it does nothing to this photon, but it's going to do something to this one here. And so the action of a creation and annihilation operator is the number operator. And so there's just going to be 1. But we're going to pull out sort of half of the phase here. So this would have been e to the I phi, but we're going to pull half of that out. So e to the phi over 2. So we're left with a half of that phase here and a negative of that here. The reason we do that will be clear in a second, but we're now going to pull this vacuum state back in, and then we'll apply the action of the creation operators onto that vacuum state. So the second rail creation operator acting on the vacuum state, that's our logical 0, and the others are logical 1. And what we can now see if we pull out, we look at the action, or maybe I'll say it like this. If you look at this line, it's sort of clear how it gets, you can go from here back to here. So if you apply this operator in, so this operator here with the sigma z, if we apply it in here, sigma z on 0, you're going to get an eigenstate of 1. Sigma z on 1, you're going to get an eigenstate of -1. So you apply these in and you get that. So that's sort of how we pulled it out. Pulling out operators sometimes can be tricky because you sort of need to go back and maybe just check that, okay, if I go back the other way, does this operation actually give me what I originally had? But if we look at what we have at the end here, we have this global phase that's being applied. So, I mean, it's fine as long as we keep track of global phases, we're okay. I mean, if it was only a 1 qubit experiment, we wouldn't even need to do that. But we have this global phase here, and it's proportional. Like, we know how much it is because it's this parameter here that we control. And we've applied, we can see here, a Pauli Z gate. And the degree to which we've applied this Z rotation will depend on the phi. So something very similar to the Y gate, we're going to use beam splitters. So this can be done with a partial mirror. There's also ways you can do it with 2 triangular prisms that are connected together. But we can just think of it as a partial mirror. So the two rails come together now. The partial mirror is here. We've seen this before. There's going to be some reflection and then some transmission, and then they go about, on their way. So we have our beam splitter. The one we worked with earlier had a pi by 4 in here. That was a 50-50 beam splitter, but we'll stay general and we'll just use theta. But we're still not going to add any phase, so the phi will still be 0. And the calculation is, it's mostly the same. You go through and you sort of go through the logic of it in the same way we did above. So I invite you to do that. And what you're going to get is you'll be able to pull out this cos theta, the identity, plus I sine theta of y, which is just equivalent to e to the I theta sigma y. So then we've had applied a y gate that we can parameterize with this theta. So with these two tools together, we can achieve universal single qubit control. So 2-qubit control. This is sort of where things get interesting with LOQC. So we're going to build up our 2-qubit gate in 3 steps, 2 of which I'll go through the details of here. One of which, if you're interested in, I invite you to look at the text on it. But I think the most interesting parts of it are what we're going to go over here together. So the first step is we're going to create a probabilistic control Z gate. So we're going to create a controlled Z gate, but it's only going to work 1 in every 16 times. And it's going to be random. So when it fails, it bombs the whole computation and we're in trouble. So not particularly useful. You have a bunch of controlled Z gates in your quantum computer. It's randomly going to work, and very rarely is it going to work. This obviously doesn't scale well at all. However, we can improve the probability of success with quantum teleportation, and I'll go over quantum teleportation briefly for those who didn't take 710. But really the idea is we want to use teleportation to take this problem of creating a probabilistic controlled Z gate during the computation to a problem of creating it before the computation. So we create it offline. And then we use teleportation to teleport it onto our circuit, but only when it actually worked. However, teleportation can't be done perfectly with linear optics. And so we still have a probabilistic gate, albeit one that operates with a much higher probability. And then this element I won't go over here is that you can actually use quantum error correction to reduce the resources needed. So one thing I should say on point 2. So we can improve the probability of success with quantum teleportation. And we can actually keep adding more and more resources to keep improving that probability of success. But the amount of resources doesn't scale well. So we use quantum error correction to improve the rate at which our extra resources scale. So let's build up to the probabilistic control Z gate. So before we can build that, we need to build something called a nonlinear sign shift gate. It's my notation for it here, NS subscript -1. So say we have some psi, and it's a superposition of state with 0 photons, 1 photon, and 2 photons. And what the nonlinear sign shift gate does is it leaves these 2 states alone and it adds it flips the sign here. So it takes us from this psi to psi tilde. To be clear here, so I put little Q's when we're talking about the encoded qubits. These are not encoded qubit states. So this is not the dual rail encoding. The nonlinear sign shift gate, or our ideal nonlinear sign shift gate, acts on a single rail, and that rail has 0, 1, or 2 photons in it. Okay, so this isn't this 0 doesn't mean the logical 0 state, which is a 2-rail state. This is a single rail. So the nonlinear sign shift gate, I mean, its name might give this away, but it's nonlinear. And so it can come from a combination of linear things. So phase shifts and beam splitters alone aren't going to cut it. But this is how we can do it. And we can do it with using two other ancillary photons, and with using measurements. So we have our psi, and we have two other photons that you can imagine two other rails. And one of them has one photon in it and one has 0 photons in it. So this is the picture here. So we have our psi here. We have, and that's in the first rail. In the second rail, we have one photon. In the third rail, we have 0. We're going to have a gate that acts on all three of these rails. And if we only look at its effect on the first rail, we'll see that it's the nonlinear sign shift gate. So this box here is going to be our, it's not, it's more than the nonlinear sign shift gate. It's a gate acting on 3 qubits, in which if you only look at its effect on the first qubit, you get the nonlinear sign shift gate. So these two photons come in, we act on all three of them, we toss away these other two that came in, and what we have at the very end is the action of the nonlinear sign shift gate with a catch. What is that catch? Let's open up the hood of this box here. What it's made of is a phase shifter and 3 beam splitters with different parameters for theta and phi. These are in the text, but I couldn't really fit them on the screen, and you can understand this fine without knowing the exact angle. So I'm going to tell you what it does. So what you do is you create this 1 and 0, the 1 photon and the 0 photons in here. They go through this operation, and the overall effect of this whole action, this whole unitary operation, is this matrix here. I just put that in there because there's a problem in the text which uses the nonlinear sign shift gate. So this is what it looks like as a unitary matrix. Now, the nonlinear sign shift gate this whole operation of ns sub x only gives our desired effect here if we measure a 1 here and a 0 here. There's a 50-50 chance, 50-50 chance. We get a 1 in 4 chance of having our gate. So we have a probabilistic nonlinear sign shift gate. What's nice, though, is that we know when it works and we know when it doesn't because we've taken the measurement. So what do we do with that? Well, we can take 2 of these nonlinear sign shift gates and a beam splitter to create a probabilistic control Z gate. So now we're using the dual rail encoding. So these 2 rails correspond to 1 qubit. These 2 rails correspond to another qubit. The second rail on each of these qubits just minds its own business. The first rails of each of them are going to interact. So they're going to come together through this beam splitter. And then next, we're going to use a nonlinear sign shift gate on each of them, and then another beam splitter. There may be a problem that you guys will be asked to do on showing that how these combined create a controlled Z gate on the dual rail encoding. So if you have any questions on this, please let me know, because I just want to make it really clear which photons are interacting. So here we have 4 photons. It's only the first and the third one that are going through any of these operations. However, to do the nonlinear sign shift gate, we need to introduce these intermediary photons that they're initialized to a certain state, they enter this action, they come out, they're measured to be 1 or 0, and then they're just discarded. We don't use them anymore. So we have our 2 dual rail encoded qubits. And so it's probabilistic because it only works if both of them measure 1 and then 0. So we have, like I said, there's a 1 in 4 chance for each of these. So in total, we have a 1 in 16 chance. But at least we know when it fails. So as it is, a controlled Z gate that works 1 in every 16 times isn't going to help us. But we can make it useful with the aid of quantum teleportation. Now, people who took in 710 or taken 710 will already be familiar with quantum teleportation. But for those who haven't, so what quantum teleportation is you can use an entangled pair to teleport a qubit of information. And what has to be clear there is that it's not like I mean, maybe this is obvious, but it's not like physical matter being like transported over there. It's not like your photon disappears and your photon reappears someplace else. It's the information encoded in your photon that's being teleported. So what we're going to use for it are something known as the Bell states. So this is a Bell basis. It's a basis for writing 2-qubit states. And so we have the 4 orthogonal Bell states. And we have 2 parties known as Alice and Bob. And so I'm going to go over the protocol of how Alice sends her qubit, so this 1, sends the information in it to Bob. So Alice and Bob have met beforehand, and they've taken an entangled pair of photons. Alice has kept one of them, given the other one to Bob. They go about their separate ways. So their joint system, so the system of Alice and Bob together, okay, so this is a spatially separated system. Alice has 2 of them qubits, Bob has 1, they're separated apart, is psi, tensor, and the initial entangled qubits are going to be in this state here, this Bell state. Alice then goes and does the measurement on her basis states. And what happens then is that we have a new state. There's some, she did a measurement in a Bell basis, so she's gotten back one of these 4 states, so it's one of these Bell states. And Bob's state is now in some psi tilde state. Bob doesn't do anything to his qubit just yet. What he does is he waits for Alice to send Bob 2 bits that correspond to which Bell state was measured. So is it the 001, the 01, the 10, the 11, where these 2 numbers are just a label. Sends these 2 bits to Bob, and Bob does one of 4 things, depending on the bits Bob received. So if Bob receives 00, does nothing, does say 10, does a sigma z, 4 different options. After applying that gate, what Bob will have is the initial psi, and then Alice will just have some Bell state that she's measured. So by sending 2 bits, so by having an entangled pair they shared originally, and by sending 2 bits of classical information, Alice can transport 1 quantum bit over to Bob. So we're going to take advantage of this. So how do we do that? So the idea is to teleport first and then use the control Z gate. So let me draw, well, previously drew. So let me show you a picture I drew. And this is one I actually drew. Lots of the pictures I took off Wikipedia, but this one I made. Okay, so we have our qubit here. And I'm writing everything now in terms of logical qubits. So this line here, you can think it's your 2 rails, but I want to keep the picture simple. So everything here just in terms of qubits. So this is our 1 qubit. This is our other qubit. Now, a very convoluted way to do a controlled Z gate is to use a pair of Bell states, have our 1 qubit moving along, use this Bell state to teleport it over here. Remember, use the classical communication to determine whether an X or a Z needs to be applied, and then use the controlled Z gate. So all this stuff in blue, this is just the teleportation protocol. This is using the Bell state, the entangled state here, and using applying an X or a Z or both to teleport the qubit from here to here, okay? So that's all we've done is we're like, hey, instead of doing a controlled Z gate on these 2, let's teleport them someplace else and then do the controlled Z gate. Seems kind of strange, but you'll see why in a moment. What we're now going to do is we're going to add 2 more controlled Z gates. So far all we've done is make the picture a lot harder. We've taken the process of doing 1 controlled Z gate and turned it into 2 controlled Z gates, a teleportation, and then another controlled Z gate. Remember, controlled Z gates are unitary, and so 2 of these back to back is going to give us nothing, just the identity. So this doesn't change our circuit at all. But now we can reduce the circuit And we can simplify the controlled Z gate and these operations of the X and Z here. And they actually reduce to something that doesn't consist of controlled Z gates. Controls of, instead of conditional X's and Z's, we have a different conditional operator. So here we have a conditional XZ and a conditional Z, conditional XZ and a conditional Z. But you can now see the controlled Z is in this green region. And this green region is stuff that we could drag this further back, like pull it way back here, and do all this stuff in the green region before the experiment even starts. Now remember, our probabilistic control Z gate, we know when it works and we know when it doesn't. So we just do the controlled Z gate, on average we have to try it, whatever, let's say however many times we need to do it. Say you have like some better protocol, but whatever, it's probabilistic. So we keep doing it till we get our controlled Z gate. And then once we have a controlled Z gate, we know we have it, we use quantum teleportation to be able to implement it into our circuit. The problem is that with linear optics, you can't perfectly distinguish between Bell states. And so the teleportation only happens with probability of a half. So then with this new teleportation protocol, we've improved from 1 in 16 to 50-50 chance of making it work. Now, there's ways to be able to use many more resources to improve the probability. And the probability scales as n squared over n plus 1 squared, where n is related to the number of resources we need. It's an integer that we choose. So this doesn't scale particularly well at first, but if you use quantum error correction, you can reduce the resources needed, and it makes it scale at least enough to be able to do some quantum computing with it. So that's the 2-qubit gate, and we've now achieved universal control of our dual rail encoded qubits. So with any quantum computer, we need to talk about sources of error. So one is just the failure of the CZ gate. Like we said, these things are probabilistic, and so there's some probability they're just going to fail and ruin the computation. But I mean yeah, so I'll leave it at that. Another one is photon loss. Lots of things can absorb photons. Photons can be absorbed at any stage. While you're going through some gate, it's possible something is there that absorbs it. And so you can just lose photons. And so obviously that's a big deal because it's the location of the photon in our rails that let us know where or determine our qubit state. So what is phase errors? So one thing we've assumed is that both photons have traveled through the same medium for the same distance when they're just sort of moving along. So when I just draw the rails, I'm assuming that this is the case. However, if one of the rails is a little bit longer than the other, or there's phase differences in the mediums, like the materials aren't perfectly the same, then what we can get is, if a photon has traveled along, if a wave has traveled along a slightly different path, traveled along a slightly different medium, that's going to affect its phase. So the two photons moving in the two rails might accumulate phase errors over time. Another thing we've assumed is that photons arrive at the exact moment we want them to. So say with the beam splitter, in our calculations, we saw it's different when the behavior of one photon going through a beam splitter versus when two are there is different. It's important that the two photons enter the beam splitter at the same time. If one passes through before the other, then they're not going to interact. Well, maybe interaction is not the right word there, but we're not going to get the states that we would expect. So that's something that's very important, something that's challenging. You have things moving at the speed of light, you want them to arrive at the right time. So those are the sources of noise, and we sort of then covered all the elements needed for linear optics quantum computing. There are some other interesting proposals for optical quantum computing. There's one-way quantum computing with optics, which has been proposed, and there is continuous variable quantum computing. For those who haven't decided, I don't know if it's too late to decide what your paper is going to be, but those are, I think, both interesting areas to maybe write your term papers on. But yeah, so that's it for LOQC. We're now going to look at how optics can be used for quantum cryptography, and in particular, quantum key distribution. I put the IQC logo there because Two of the slides in this presentation I took from the outreach materials we use. So just wanted to give remember to give a shout out to John Donahue for making these the slides when we talk about the BB84 protocol. Okay, so we're going to look at quantum key distribution first. And I think one thing that's worth saying is that, even though we started with linear optics, quantum computing, and today we're probably going to spend about an equal amount of time talking about optical quantum computing and optics used for quantum cryptography. That's not to say that the two fields are equally developed or that they are playing as equally important of a role in the development of quantum implementation devices. Right now, if you were to go and to search through the literature on optical implementations, you're going to find more work being done on quantum cryptography, and you're going to see more recent developments, or more of the developments reaching a stage in their maturity in which they're being used by wider cross sections of the population with cryptography than with quantum computing when it comes to optical implementations. And that's just, how it currently is right now. So I just want to really stress that the importance of optics with quantum cryptography and with quantum key distribution, that it is it's the implementation of choice for quantum cryptography, and optics has played a huge role in quantum cryptography. So I've pumped up its wheels enough, we can start talking about it. So say you have some information and you want to send it safely to a friend. So say you're in elementary school and you have some note you want to send. You say, hey, how's it going? Pass the note to your friend. Well, if your teacher intercepts that note, reads it out to the class, you'd be humiliated. So you want to keep that information secure. So what you do is you come up with some type of secret translation. You have some key that you use to encrypt your message. So for example, you say, whenever I write A, I really mean D. When I write E, I really mean X, et cetera, et cetera. And to anyone else besides you and your friend, the message is just gibberish. So what would that look like with computer language? So we're using binary. So you have some message of zeros and ones. You have some encryption key, and you use binary addition to create your encrypted message. So this is the message that you pass. You pass the message to your friend uses the key and is able to, again, through binary addition, get back the message. So this is a great way to keep information secure. The only problem is getting the key. So you want to send this key to your friend in a secure way. You can't just, email the key, because then you need something to protect the key. So you need like a key for your key. You need a key for that key. And that'd be terrible. So you need some kind of secure way to transmit encryption keys. So that's the flaw with this. So one way to do it is through the BB84 protocol. And what it does is it uses incompatibility of different measurement bases to be able to securely transmit a key. I put here in brackets not entanglement, because I think that's one of the main misconceptions, or one of the first misconceptions of the BB84 protocol, is that it's entanglement that's the resource that allows you to securely submit the information, but it's not that. So I think the easiest way to understand this protocol is just to see it in action. So this is the slide I took from the outreach programs at IQC. The only change is I used Bob Ross here. I figure if you have the choice to choose any Bob that you want, the correct answer is going to be Bob Ross. So anyways, we want to create a key. So we're not sending a message here, we're finding a way to securely send a key. So Alice chooses a random bit, 0 or 1. Alice then goes and she chooses a random basis. So here we're going to be using the polarization of light. So Alice is going to choose the horizontal and vertical basis to send her photon in. So it's polarized horizontally or vertically. And so because it's a 0, it's going to be horizontal, a 1 is vertical, and that's just the choice of encoding made here. So what Alice sends is a horizontally polarized photon to Bob. Bob is going to measure in a random basis. Let's say Bob is just lucky and measures in the right basis. Bob's going to get the right polarization and get the right bit. But if we do this again, say Alice chooses a random bit, this time it's 1, chooses a random basis again, so horizontal and vertical, this time sends vertical light, vertically polarized light. Bob goes to measure the photon and measures in the wrong basis. I mean, it's random, he's a 50-50 chance of getting it right. What Bob's going to record then is a random bit. Might be right, might be wrong, we don't know. But what we do know is that it's random. So we'll just leave it as random. Alice does this again, 0, chooses the diagonal, anti-diagonal basis. 0 here is, I don't know, whichever one you want to call diagonal, anti-diagonal. Let's say this one is diagonal, that one's anti-diagonal. So sends diagonal to Alice. Bob happens to measure it right, gets the right bit. You do this many, many times. And what you do then is you take a classical channel. So right now, this is all quantum. They're using a quantum channel to send a polarized photon. They're sending single photons. They need to use a quantum channel. Let's say now that Alice and Bob also have a classical channel in which they can share classical information. What they do is they compare the bases that they measured in. They don't compare the bits they got, because if they save their bits over the classical channel, their information is done. Well, I mean, it's no longer secure. So they go and they check, okay, did we have the same first bases? Yeah, third, yeah, fourth, okay, etc. And they only keep the ones where their bases match. So if Alice and Bob had done this protocol, for this many photons, the key that they both have would be 00100. And they never had to exchange any classical information to be able to transmit this key. So this seems at first like amazing. Like, okay, great. We had no problems and we can send a key however we like. Life is good. However, there is a bit of a catch. Let's say you have an eavesdropper or an eavesdropper. That's for any other Pokemon fans besides me. 25th anniversary was yesterday, so shout out to Pokemon. So we got Alice and we have our channel, and Alice is sending a message to Bob. And we have our eavesdropper, EV. It's the last time I'm going to stress that joke. I'm just going to refer to them as Eve now. So we got Eve there, and Eve is listening in. So what can Eve do? How can Eve, by listening in on the quantum channel, steal information? So Eve listens to the classical communication, and there's no information there. It's just random bases. That doesn't help Eve. But what Eve could do is intercept Alice's photons, measure it, and send them to Bob. So what happens if Eve does that? Well, 50% of the time, Eve is going to measure in the correct basis. Eve has the same odds that Bob does, and Eve's going to steal that information. And then you can pass the photon along, no problem. The other 50% of the time, Eve's going to measure in the wrong basis and is going to get nothing. It's going to be a random bit. And Eve's going to corrupt the information and send it to Bob. So now when Bob and Alice go to compare bases, there could be times where they had the same bases, so their bits should agree. But because Eve was eavesdropping and did a measurement in the wrong basis, Eve corrupted that bit of information. And so now they don't have the same bit, even though they measured in the same bases. So what do? Well, the simplest security around it, and it's sort of the first step of making this process more secure. Oh, I just realized I spelled security wrong. My bad. English is my second language. I use that as an excuse, even though I've been speaking English for, I don't know, like 15, well, no more, 20 years. But anyways, security issues, my bad. So the simplest security one would be that, yeah, Alice and Bob take a portion of their key. So this is after they've done the protocol, they've made their key, everything's good. They take a little piece of it and they'll compare that publicly. So they're just going to throw that away and they're not going to actually use that because they're comparing it publicly. If they see that their keys disagree above a certain threshold, then they know someone was eavesdropping. If it's below a certain threshold, then that means there wasn't an eavesdropper, but there was just some error there. So, well, there's two issues. So one issue is that photon detectors have some noise. So like I said, even without eavesdropping, Alice and Bob's bits will differ. Another issue is that if your source gives more than one photon, so say you don't have a perfect single photon source, Eve can split the pulses and observe one photon and give the other one to Bob. So there are some things you have to, there's at least impetus to make this protocol more secure. So we do that with essentially all classical tools. None of this post-processing work to make our key more secure needs any quantum channel, and it's just classical. So we've used the quantum and classical channel to share a key, and then we're going to use just the classical channel to refine the key. So first we're going to detect and correct errors. This is called information reconciliation. It's a way to correct errors that, I mean, could have come from the noise sources we said. I mean, that's ideally, that's what it is. You're assuming there's no eavesdropper, and you're just trying to decrease the amount of errors that have come from the key. If you did have an eavesdropper, you would have noticed it when you shared the keys. But yeah, so you're just trying to improve the Alice and Bob's keys to match. However, when you're doing this information reconciliation, you're going to introduce some information leakage. So you're going to communicate a little bit, and through that communication, Eve can deduce some more information and use that to figure out what the key was. And so we can mitigate that leakage with something known as privacy amplification. So together, what you do is you begin with this partly private key that you generated together that maybe had someone had eavesdropped a small amount of it, so little that you didn't notice. Also, there was some disagreement because of the noise. And you take that and you get a smaller, more secure key with less errors. So first we'll look at information reconciliation. So we start with this assumption that Bob is a noisy key. And the goal is to correct Bob's errors. So say this is the key Alice sent, or meant to send at least, and this is the key that Bob found through the BB84 protocol. 3 of them don't agree. So the classical channel they're using to communicate now, we're assuming this classical channel isn't secure. And so this protocol is going to be able to, okay, a better protocol will be able to reduce the number of errors without giving away too much information over this classical channel. So you want to limit the ratio of the number of bits revealed to the length of your key. So if you had, you know, a billion digits in your key, and you give away like a few hundred, not a big deal. If you had, you know, 500 and you give away a few hundred, I mean, your key is useless. So one, like a simple way just to illustrate how this could be done is you could do a random parity check of bits. So you essentially ask, you know, are qubits 7 and 8 the same? You're not saying what they are, but are they the same? Well, if they are the same, good. If they're not, then you just throw them both away because you don't know which one is the one with the error. This is somewhat inefficient, like you're burning through a lot of bits doing this. There's a more sophisticated scheme, and one of the first ones, and it's called the cascade protocol. There's sort of 2 stages, at least conceptually, to the cascade protocol. We're going to look at one of them here, and that's going to set you up to be able to describe the second one in a homework, in a problem set. Not certain if it'll be in a problem set, but it's one idea for a problem set question. So I'm going to show you the first part of the cascade protocol, and you'll get an understanding for how it works and why it works. And I'm going to leave the second step for now, just in case we include that in the problem set. If we don't, I can show you how it's done. Okay, so part one of this cascade protocol. So, and maybe it will be, second part might be in problem set 4. Okay, so Bob shuffles his key to try to randomly spread out the errors. I mean, this isn't random in random that he doesn't know, like it's some mixing that he's aware of the original position of each of these keys. So he can unscramble or unshuffle his key if he needs to. So the keys then broken into blocks. And so the size depends on the error rate. Your goal really is to try to have each of these blocks to only have one error in them. So you want to choose the size small enough. But the issue is the smaller you choose the size, the more information you're going to give away to Eve. So you just are trying to optimize based on your estimated error rate. So what you do then is you check the parity of each block with Alice. So this protocol is really on Bob. Bob is the one who is going through the steps of it and is really just communicating with Alice and asking Alice questions. So Bob goes and checks the parity of each block with Alice. Says, okay, your first block, sorry, I should say one more thing. So this shuffling procedure, Bob has told Alice this shuffling procedure too. So Alice has also shuffled her key. So they still have the same key. They both shuffled it in the same way. So Bob says to Alice, hey, okay, block 1, and by comparing the parity, can determine if they have an even or odd number of errors between them. So the issue is if they have even number of errors, it could be 0, it could be 2, it could be 4, you know. So they don't know if there's an error there or not. So they leave it. But if they check and they see that Bob sees he has an odd number of errors, so 1, 3, 5, telling you guys what odd numbers are. Hope I didn't insult your intelligence there. But anyways, he knows that within this block, there's an odd number of errors. Here, Bob doesn't know if there's errors or not. And so by learning this information, with even, Bob will do nothing. With odd, Bob will use a simple binary algorithm where Bob splits it in half and checks the parity of each, splits it, and then the one that's odd again, splits that in half, checks the parity of each, until Bob gets the one bit that was wrong. And here Bob can, either correct the bit or just Bob and Alice both discard that bit that was wrong. By discarding it, they can limit the amount of information that Eve is able to take from them through listening to their communication. So they don't leak the key, but they are leaking some information. There's some information of which blocks have similar parity. And Eve also knows the shuffling. Really, the shuffling isn't for more security. It's just to try to spread out the errors as best they can, in case there's like some, systematic reason why errors during some period of time built up. Say like the channel was like faulty for some time or whatever it may be. And Bobbin will then repeat this protocol with Alice, but now use larger blocks. So assuming that, essentially repeat it again. So I won't get into too much of the details of the bigger blocks, but that's something you'll potentially show in problem set 4. And yeah, as I mentioned, you can disregard the last bit instead of correcting the error. So that's one way to make the key, Bob's key and Alice's key more similar. And ideally, you would get them to the point where they're essentially, exactly the same. That's the hope, at least. So what do you do now, though, that you have this key? It's now more exact, but you have the problem that Eve has gathered more information now. Even if Eve wasn't eavesdropping at first, Eve could have gained information, or maybe Eve was eavesdropping at first, but only gained a limited amount of information so that Eve doesn't know, you can't detect that Eve's there. Like the degree to which Eve messed with your information is on the order of how much error would have come just from the noise. So how do you deal with this cute little one? Well, Eve has information. Could be from the original eavesdropping, could be from the parity info during reconciliation. And what you essentially do with privacy amplification is there's different ways which you use your current key to produce a new shorter key. And it's based on how much information Eve could have gained. So you can create, based on how much you've communicated, you can create an upper bound on how much information Eve could possibly know. Based on that upper bound, you can determine how much information you need to throw away for Eve to not be able to know what your key is. And there's different ways to do it, but the idea is just the same. It's just some kind of compression function. So an algorithm that's used to eliminate some amount of bits, it's the same bits Alice and Bob are removing. So there's different ways in which you can choose how to do that, but the idea is really just the same. It's you're removing bits. So I believe that is it. That is. So that is it for linear optics quantum computing, quantum cryptography, based on the foundational things we had. As always, feel free to come to office hours or to ask me questions during the times. I'll be doing sort of like a bonus office hours, if you will, during the regular lecture hours, because this is going to be posted before lecture. And you can come to those hours with your questions from the video, and we can chat about them. Or if you can't make it to either for some reason, just post on Piazza, and I'll get back to you.